So my pleasure to introduce Professor Robert Heath, NC State, from NC State, although most of us probably associate his name with UT Austin, where he was for almost 20 years until 2020, and where he developed a lot of contribution to the community of wireless and also through another initiative, which is the MIMO wireless, which he was president, he's president and CEO. The research interests of Robert are wireless communication, cellular system, public safety, military networks, a lot of things. So we're glad, of course, also 5G, 6G, and whatever is related to that. And so I give the floor to Robert for his talk about beam training in V2X, leveraging machine learning.
All right, thank you for the introduction there. Just trying to set up my screen here. Let's see. So I hopefully don't go too long here. But yeah, let me go ahead and get started. So yeah, I'm happy to be here. And I kind of wish I could, of course, be there. The food is a little bit better in Paris than in Raleigh, turns out. Not that it's too bad here. Yeah, so I just joined NC State about 18 months ago. It's been a great ride so far. You know, loving the environment and the new opportunities for collaborations. And you might have heard a little bit about this yesterday, but I'm excited to be a part of an initiative that we've created with Professor Gonzalez-Prelchich on taking wireless forward to 6G, and we call it 6G NC. We kicked this off last year, and now we have a number of companies that are funding research, including Docomo, Maxcentric, Nokia, Satsui, Motorola, Texas Instruments, Toyota, and Hughes Network Systems. There's a lot of interest in looking at research that's not just in signal processing communications, but also that goes down into antennas and circuits, as well as up to networking. And as one of the exciting parts about being at NC State is that we have a really rich circuits and antennas group that, as you've seen from the previous talks, like the one on terahertz, that there's increasing need for more collaborations between those of us that work on systems and more from a mathematical perspective to work with the people that are actually developing the hardware as a means of deriving new and appropriate mathematical models. So it's something that I think that we're well equipped to do, and our sponsors are already recognizing this and in the work that they're supporting. So I'm happy to be invited in this particular workshop because I have worked on the vehicular applications of wireless for a number of years. Before I left UT Austin, I was founding an initiative there called UT Saves, which was combining communications, sensing, and machine learning. And so through that initiative, we and other faculty collaborators, we worked a lot with automotive companies, Texas Department of Transportation, Federal Department of Transportation. And it was an interesting experience to have the opportunity to work in a specific application vertical and to learn what is important from the people that are running the application, in this case, a transportation system, and how that differs from the kinds of work that we do in wireless. So I'm going to start off by just talking about the beam-based MIMO architecture, which is a key component of 5G and possibly will remain in 6G as well. And this has got material that comes from some tutorial presentations done with my colleague, Professor Gonzalez-Prelchich, as well as some other material I've given in the past on machine learning. And there's another tutorial you can check out here after the talk. So the motivation for looking at MIMO and this beam-based architecture, it comes as follows here, that there's a lot of interesting opportunities for communication in V2X networks. And since I'm joining in the second day, I assume you've seen already a number of these applications mentioned, but essentially there's opportunities both for supporting higher throughputs. And you can see here in this illustration how there's a nice scaling of depending on the throughput that you have available for a vehicle, it becomes possible to exchange more sensor data, less processed sensor data, and so the vehicles can exchange more of this with less potential processing. And if you add up the requirements from the number of typical sensors on a car, you can easily get up into the hundreds of megabits per second, if not gigabits per second. It all depends on the kind of compression that's working. So there's an opportunity for higher throughput. Now, at the same time, there's also interest in low latency communication. And if you can potentially bring the latency down on the networks to even sub-milliseconds, you can start talking about having the network taking control of the vehicles versus the vehicles being driven autonomously with like computers in the vehicle itself, or of course being driven by people. And while you may not believe in wireless enough to want to have the car driven by the network all the time, I think we all as wireless engineers have a fair amount of skepticism of that, but there are certainly places where it would make a lot of sense, like intersections as an example. If you have low latency, you could imagine handing off control of a car to an intersection controller that orchestrates the cars going through the intersection, just like a wireless scheduler schedules packets. And so that becomes possible with low latency. And you don't necessarily need the combination of low latency and high data rates for every envisioned application of V2X. I mean, but certainly there are different parts of the vehicular system that can benefit from one or the other here. And then we see that there's a number of places where different wireless, in particular MIMO technologies, play a role as a function of the frequency. So the high data rates can really only be supported, the super high like throughputs at mmWave or higher frequencies, while the lower rates might be better supported at a lower frequency sub 7 gigahertz solution. And so you see applications of single user, multi-user, massive MIMO, mmWave MIMO. The ones I'm going to talk about here, I'm going to touch on both mmWave MIMO as well as lower frequency massive MIMO communication. And then all of this is exciting for the vehicular case because it really is pushing the limits of what even can be done by 5G right now. And it's one of the reasons that vehicles, though it was a really hyped topic, didn't become a big part of 5G. And even in the latest release, the full capabilities are not brought to bear on the vehicular application. And then I just wanted to put a comment here that, while I'm going to be focusing on traditional, perspective from signal processing and communications, we have to remember that at the end of the day, whatever's on this chart here really doesn't matter, because the actual performance objective is more related to safety and traffic efficiency. We want to design a transportation network that gets people between 2 points as quickly as possible. And of course, we don't want those people to crash and die. So those are the metrics. And it actually is shockingly hard to translate those metrics down into something that is meaningful from a theoretical perspective. And we tried to do this early on, and then, we ended up just focusing more on the models because it was just too difficult. And yet all the people we talk to, like in Department of Transportation, they don't care about gigabits per second. They just want to know, okay, how is this going to improve our network? So the focus here on MIMO, and up until say 7 years ago, was in this sort of conventional MIMO architecture, which is what was used in LTE and is part of what's supported in the lower frequencies of Wi-Fi right now, where there's a bunch of antennas connected into the digital through mixed signal and RF components. And in principle, the transceivers have the ability to exploit all the spatial dimensions by they send training, there's feedback, there's channel estimation, there's beamforming, and you can do spatial multiplexing, the usual kinds of MIMO operations across all of those antennas. And the main drawback of this approach is that you need to excite all of the antennas with training sequences in order to estimate this high dimensional channel. And that puts, because of, especially in the vehicular setting where coherence time is limited, that puts a limit on the number of antennas that you can realistically support in such a system. And so the benefits of MIMO in this kind of a setting here don't obviously scale to the support of high rate, high mobility settings. So what is alternative? So the alternative that we started looking at probably 2013-14 timeframe is this hybrid MIMO architecture, which is a generalization of an analog beamforming approach, which has been a part of array processing for a long time, where some of the spatial processing is split now between the analog domains and the digital domains. And so you can imagine that in the analog domain, there's a network of combiners and phase shifters and attenuators that is being used to create one or more beams. And then those beams are potentially further excited and pre-coded upon in the digital domain. And so you have a digital that takes data, spreads it across multiple beams, and then those beams are formed and further formed and adapted in the analog domain. And the special case of this is where you have a single beam in analog, and then there's not any interesting digital pre-coding, but you're just focusing the beam as if it's an adaptive antenna. And the challenge of this architecture is that, first of all, the benefit is that you can scale the number of antennas without overwhelming the overheads required for channel estimation feedback potentially, because you can have here, many antennas that are used just to form like one beam or two beams. So then the dimensionality of this digital part is quite low. And these large antennas are really good for millimeter wave and terahertz, just for purposes of getting array gain. So that's the plus of this. The negative is that from a digital signal processing perspective, we still have only the ability to measure what's happening on the digital side. And so it makes it hard to, you essentially observe, if you send training over here on the digital, and then you make measurements here, you observe a low dimensional, a compressed version of this high dimensional, spatially, frequency, time selective channel. And so it becomes much harder. So while you're reducing dimensionality as a plus, in some ways, it's also a negative in that you don't have easy access to the high dimensional channel to do the usual kind of MIMO processing. And so the typical approaches for dealing with this, the one that was adopted in 5G and 11AD and 11AY is called beam training, where the transmitter and receiver try different configurations of the analog and then use the one that works the best. And so instead of trying to estimate the channel, you just try to find approaches that work well on the channel. And that has some drawbacks, as I'll explain later. The other approach would be to take something that's more principled from as an example, using compressive sensing and to do compressive channel estimation. It's another topic that we've done a lot of work on. And there, that is not supported in the standard, but it's another approach. And the approach there is to try to use a specially designed sequence of measurements to uncover the high dimensional MIMO channel, and then to do the configuration based on the estimate of what's in high dimension. And even though that wasn't supported in 5G, I think there's still a lot of opportunities for that to come in the next significant release of the standard in 6G. So what 5G has done to support that analog architecture is they've adopted what's called a beam management framework. And to me, this is the main, conceptual physical layer difference between 5G and 4G is really this in how the MIMO is done, because it's not really the access strategy. OFDMA was used in both cases. It's a little different in 5G, but there wasn't a huge change there. And so the principle of beam management is that there's an initial access phase where the base station is sending pilots on different beams. The user is possibly listening on different beams. And then by trying different combinations of beams, the user and the base station can agree on one or a few that work well. And then there's optional further refinement stages at both ends. And just to break it down a little bit more, there's multiple phases of this process. The first phase, sending the pilots for each beam, there's a specially designed waveform for doing that, which allows the device to do synchronization, channel estimation, and to measure the signal strength of those beams. So there's a beam sweeping phase, a measurement phase, and then there's a phase where the device determines which of those beams are good, one or more, and then reports that back. And the real downside of this is that there's a lot of potential overhead associated with measuring the beams. I mean, so to get the best performance, you probably need a lot of beams, but then you also need to make a lot of measurements. And then while the system can work where a single beam is exploited at the transmitter and receiver, it works better if a few beams are fed back and there's a stage of pre-coding or combining across those beams, and that would be the hybrid architecture. So that's and then so that's one of the main challenges here. I mean, is just the dealing with the number of measurements and dealing with the trying to figure out how to use the reported measurements for good performance. So I decided to break up some of the key functions that I'm going to talk about in the time remaining of beam management. So some of the features here, things that can be decided in the process of doing beam management. One of them is the beam codebook, the actual beams that are excited either at the base station or the user. In 4G, the codebooks that were defined there were codebooks primarily for feedback purposes, and those were fixed and predetermined as part of the standard. In 5G, because of this decoupling between the analog and digital, the beam codebook there's not a mandatory set of beams to use. I mean, the default one that people use is a DFT codebook, but that's actually left up to implementation. So the beam codebook is something that can be designed and adjusted. You don't have the ability to change the maximum number of beams. That's a function of the frequency. And then the beam sweeping, well, when you have a set of beams, you can measure those beams. So that's part of the overall overhead. Similarly, at the user, the beam codebook can be designed. There's a beam measurement phase, there's a feedback phase, and then based on what's fed back, there's a pre-coder determination. And so the parts of the problem I'm going to look at today, I'm going to look at approaches for reducing overhead that involve reducing the number of beams that need to be swept. And we're going to use site information to do that. I'm going to look at approaches that use, and that's leverage, that's going to be exploited by machine learning. I'm going to look at approaches for designing better beam codebooks for both millimeter wave and lower frequency systems that make that process work better. And then I will wrap up with a description of a system that doesn't require changes to the way that 5G works now, and proposes an approach for using machine learning to design a better code book that gives a substantial improvement over what would conventionally be done. So I'm going to start off with just talking about why machine learning is interesting for this problem. So there's a lot of opportunities specifically in the vehicular context for exploiting machine learning. So this is summarizing the aspects here. So first of all, there's this aspect of regularity of the environment. I mean, the vehicles are driving on the same roads. Presumably they're not driving on the sidewalk and doing something crazy. So there's a lot of regularity. There's a lot of regularity of patterns, different times of day, different traffic conditions. The orientations of antennas on the car is typically fixed. And so there's a lot of less kind of variability versus having a handset, which could be in someone's hand in different ways, in their pocket, in their bag. And there's also a lot of side information available in the form of location information, radar, cameras, LiDAR. I mean, this is all sensors that are used on the vehicles to support automation, and those sensors could be used as well for communication. So that's so essentially it's a lot of data and a lot of potential correlations in that data that can be exploited. So a second topic here is that there's also a fair amount of computational capability that can be available in the car that perhaps wouldn't be available in the handset. We're not going to exploit that too much. We're primarily going to be imagining that the machine learning that I'm talking about here is working at the edge and the base station anyways. But some of this could be pushed into the vehicle itself. And then finally, just there being a lot of regularity and a lot of past data that generally is available in wireless systems to be exploited. So that's the general play for looking at machine learning and wireless, and then specifically in the vehicular context. And the way I like to think about it is that there's a lot of correlations, and it's hard to analytically derive expressions that would capture all of those correlations. And so we use machine learning as a way to uncover them and exploit them without having to have a model for how, a LiDAR here impacts communication there. And then this idea of doing things with machine learning. Well, I mean, the implementation of the wireless system, is always left up to the implementer. There's functions that are specified that have to work in a certain way, and there's other ones that are done in software, and like scheduling, for example, is not specified in the standard. What we're seeing now is that there's interest in opening up all the aspects of cellular networks in this trend called open radio access networking, and ORAN is one of the examples here, where the components are opened up so that different people could come in and make different parts, and all of those parts could interoperate together. And this is good news for a lot of smaller companies, and maybe bad news for the larger infrastructure companies, Nokia, Ericsson, Samsung, and the like. Of course, they're also getting involved too, so maybe it's good for everybody at the end of the day. So one of the nice things is by pushing a lot of these functions into more open software framework, it becomes much easier to reconfigure them. So for example, the codebooks that I was talking about earlier, which are not specified in the standard, they could be updated and changed in the software. And so then for that matter, they could be learned and updated based on the data that's being collected and distributed also in that network there. So the topics like codebook learning, codebook updating, optimizing the transmission, these are all things that would be supported in an ORAN type of an architecture. And it's one of the reasons that Meta, who is one of our collaborators in this work, is interested in this general direction, because it's not just conceptually interesting, but it's also incredibly practical. So now I'm going to summarize just in a few slides here some of the work that we did that got us excited early on about using machine learning for solving communication problems in the V2X setting. Our initial work started with a couple of projects with Toyota, where they were looking to understand the potential performance of mmWave in the V2X setting. And we realized that one of the main challenges was configuring the beams. And so we developed strategies for solving that. One of the ones that we've used that I think is quite popular now is we called Positionated beam training. And the idea is that you can use the reported position information from the vehicles through a side channel like DSRC or low frequency cellular to design a machine learning engine that takes position information and generates recommendations of beams to try. And so here you can imagine that the way this works, I mean, the car communicates with the base station and says, hey, you know, let's talk with MmWave. Here's where I am. And then the base stations could respond and say, well, okay, these are the beams you should try. And then it tries its own set of beams. And the idea is that by doing this, you can imagine having a code book with a huge amount of pointy beams, but you only end up having to try a few. And the key is finding a few beams that work well with high probability, so that you don't want like 5 beams pointing in the same direction. You want them pointing in different directions, such that you capture those corner cases, the situations where that main line of sight link is blocked and then you need a backup, even if it doesn't happen a lot of the time. And so we develop techniques to maximize beam alignment probability. And we call this inverse fingerprinting because it was like the reverse of the usual problem in wireless, where you were trying to use like channel information to find location. Now we're trying to use location to find something about the channel. And then we had various extensions of that work. We looked at a case where we had a very coarse beam alignment and then an online update stage as well. So this was good for obtaining a couple extra dB of performance. But most of the performance improvement was not in the array gain, it was in searching 20 beam pairs instead of 1,000 beam pairs. So there was a huge reduction in overhead, and then some additional performance improvements from refinement. And then we looked at other cases as well. So that scenario I just described to you, the database was built up where there was an ego vehicle and a base station communicating, but we didn't use knowledge about where the other vehicles were. But that information could also be available because those vehicles are probably also broadcasting their locations and exchanging information for collision avoidance. So then in other work, we looked at how could we incorporate information from the other vehicles. And what we found there is, one is we found some ways of encoding the information from the other vehicles in a smart way, because like not all the vehicles, like small vehicles don't matter. It was the trucks, and depending on where the trucks were, they made more of a difference. And then we were also able to reduce the number of beams that had to be tried. So we went from like 1,000 to 20 down to 4. So there is again a huge potential overhead reduction, and machine learning is critical here because we know those correlation. We know that vehicles can block the beams, but we don't necessarily have the perfect description of the vehicle, and we're not running a ray tracing in the loop kind of a simulation comparison. So that was another line of work that, and then one of the other things we found here is we did a lot of work with different kinds of machine learning, including deep learning. And we found that because of our expert knowledge about the system, we were able to engineer like a random forest at the end to work just much better than the best deep learning strategies we can provide. And I think that's a theme that you generally see in wireless applications specifically, is that there's value in engineering knowledge and that can be exploited. We did other things as well. We've looked at sensor information. This is an example where we use LiDAR as well as the location information to help predict the beam patterns. And this work with my collaborators led to one of these ITU competitions was, I think, LiDAR based beam training this past year. So the time I have remaining, I'm going to talk about 2 more sets of results. The last one I have is in more detail, so I'm just going to spend a couple minutes on this result here. So this is some of the things that we've done the last couple of years. This is with my PhD students, former PhD students, Yuyang Wang and Nitin Myers. Yuyang is now at Apple, and Nitin is at assistant professor at Delft, and then Professor Nuria Gonzalez-Prelcic. And the key idea of the problem was that we wanted to find a way to develop basically a way to exploit the beam, the spatial structure experienced at a given base station without necessarily having location information. So we wanted to, so the idea here is that like in a particular base station and just a given arbitrary beam code book, there's going to be beams maybe that don't ever get used. and others that get used a little bit, and some that get used a lot. And so the idea was to try to figure out how to redesign the codebook so that we could better cover the areas which are used more. And so, for example, this is like a typical azimuth elevation distribution for vehicles on a road, and you can see, you know, the elevations pretty focused because the vehicles are not in the buildings, they're on the roads. And so the idea was to use this information, and the specific strategy we took was, it was a modification of a particular compressive sensing approach using circularly shifted sequences developed by Nitin, and then using this kind of compressive strategy that is an efficient way to estimate the channel, and using that approach for beam alignment, but then relaxing it so that we could, instead of using like a traditional compressive approach, we could do something that is smarter and takes advantage of reinforcement learning. And we used, in this case, a multi-arm banded approach. This is, you can check more of this out in some of the references I cited at the beginning here. But the net of it was that we were able to, with a similar amount of measurements, we could outperform exhaustive beam search very quickly. When exhaustive beam search, in this example here, had around 1,000 attempts, and with like 40 attempts, we could do as well. And then we could do even better with more measurements. Now, the previous example I gave you had sort of similar numbers, but we were using location information, and we could get the same performance with about 20 measurements. So here we have no location information, but we have used machine learning to design the Beam codebook in a smart way. And now we have that same performance with 40. So I think it's quite encouraging result here. And there's some other dimensions, other directions that we pursued here in one of the other papers I mentioned there, involving replacing each of these components with something and using a deep learning framework to solve all of it. And we can reduce the effective number of measurements down even further, actually back down to 20 or so, even less with location information. Okay, so to wrap up here, I'm going to talk about this most recent work. This is part of a collaboration with Meta that one of my PhD students at NC State is doing, Ryan Joyfurst. And this is quite recent work that is just going to appear in the V2C conference in this summer. So it's hot off the presses here. What we've been looking at in that project has been similar idea of, you know, how can we do beam-based MIMO communication efficiently, but focusing specifically on sub 7 gigahertz. So at the conventional massive MIMO and MIMO frequencies in cellular. The beam-based architecture, even though it's not needed at low frequencies, is still used at low frequencies, I guess, because of consistency across having 5G work in a similar way at low and high frequencies. And so the problem here, just to explain it a little bit of detail. So we started off this study imagining a narrowband multi-user MIMO system. We have the broadband extension is in the journal version that will be submitted soon, but what's described in that VTC paper is a narrowband. And we have planar arrays at both the base station and the user. There's a clustered channel model. And there's the possibility of doing multi-user MIMO or, you know, massive MIMO type communication. What we consider is we tried to consider a setup which was as close as possible, at least as we understand how 5G works. And so we're considering a setup where there's a beam-based architecture. At low frequencies, there's only a few beams. So the number of beams is something like 8. And you can do digital, each beam can have multiple antenna ports. So you're doing MIMO channel estimation within the beam potentially. So I don't mean to say that, you know, there's only one port per beam, but there's only a few beams. And then the objective is to figure out for the base station is to figure out how to do the MIMO pre-coding design, but the feedback information from the user is going to be very limited. So the base station sending, there's an SSB beam training phase. The users are estimating the channel in that beam and then using MRC combining or some other strategy to estimate the received signal power, essentially corresponding to that beam. And then it reports back the preferred beam and the power for that beam. And we use just that here. I mean, you could imagine settings where it reports, of course, much more information and other kinds of feedback. But this is the basic setup that we considered here. And then the objective was to figure out how to design that beam codebook in such a way that based on this limited information from the users, we could get essentially good performance, high throughput in the system. We didn't look at any kind of scheduling, so basically looking at some rate kinds of performance metrics. And then in a few minutes left, I'll describe just some of the key ideas here that we used to solve this problem that we encountered and then we overcame. So one of them is that one of the biggest challenges in the codebook design is that when you make a change in the codebook, there's an ordering of the beams that happens in there. And so if you have changing codebooks over time, then there's a question is like, what does it mean? Okay, beam M in this time means something different than beam M in a different time because the codebook can potentially be changing. And the thing is, we want to design the codebook. And so what we'd like is to get some sort of underlying data that we are extracting as a function of the codebook, but is independent of the specific ordering and the details of the codebook itself. And so the key idea here was to, instead of thinking about the codebook as this distinct set of code words, that we looked at the image constructed from the beam in each codebook. And so in each code word in the codebook, which is a beam, has a certain intensity pattern. And here, just for the sake of discussion, we've drawn two, somewhat focused intensity patterns, but they don't have to be, because, we could learn beam patterns that are more messy looking. And so essentially when a user reports back that they prefer a particular beam and have a certain strength, instead of putting the beam index and the codebook, et cetera, into the machine learning algorithm, what we can do is we map that information onto a standard format of an image so that the essentially the angular regions covered in the intensity, that becomes the input. And so in this way, we're able to do this learning without having the codebook input into the learning algorithm at each step. So that ends up having that was like the first observation that we made, that after, of course, trying to solve it in a different way for many months. This took, probably this is a year of work that we're talking about here. So that was the first approach there. And then the beauty of, once you start to encode the information in imaging, then we also had to look at, okay, what's the other, potential structure in there? I mean, how can we account for, different codebook sizes? And then how can we, exploit that information? And then we also have like, shift equivalent, shift invariance kinds of properties. So how could all of that be exploited as well? And so a natural application here was, because of this and because the image processing, was to use, convolutional neural network, and the layers are shift equivalent. And so we share parameters, and convolutional neural networks basically is a means of reducing the number of dimensions to be parameters to be estimated in the network. And they have a strong inductive bias for shift equivalence. So it makes a lot of sense if you have that property to use such a network there. And then, so that was the second key idea here. And then just a little bit of details about the network itself, which the student who did this knows many more details than me about this here, but we use 2 convolutional layers and pooling, ReLU activation on the encoder side, and then 2 convolutional transpose layers, ReLU activation, and then linear layer on the decoder side. There's a grid source to tune hyperparameters, and the overall number of parameters we ended up considering was around 5 to 20 million altogether. And we defined a few different networks that for comparison purposes that are based on, so essentially the SSB information that comes back is mapped into this input into the network. And then what we're trying to predict out is either the beams to use or the precoders to try. And then, so here's and then the simulation strategy. So one of the challenges you work with machine learning is getting a data set that you haven't cooked too much, because if you cook it too much, then you just are learning whatever you put in there. So we use the Quadriga channel simulator, which allows us to get spatially consistent channel measurements, even in the vehicular setting with users and roads and off-roads and different locations. So we use that to generate a rich database of different channels. And then we do initial access simulations with those channels where we do like DFT-based beam training, there's feedback, and that information, along with the SVD beamformers that would be derived from that channel, is also fed back and used as part of the training. So while we're not going to we're not going to do the SVD at the receiver and feed that back to the transmitter, we're using this as part of the training set. So the actual operation, we won't use that. But what we're trying to do is to figure out how to get the best performance from just the RSRP, and essentially to be able to predict the SVD beamformers and the best codebook that should be used. And then here's a little timing diagram here. So there's a particular codebook is chosen, there's measurements across the codebook, user feeds back the best response. And then once it feeds back, the base station does multi-user MIMO, using the machine learning algorithm to help to produce the predicted beam pair. The resulting performance of that whole thing comes back, and then that information is used to generate a new beam codebook that will be used in the next time frame. And then one of the things about all this is, because we were working with Meta and trying to do this in a real system with real data, is that we had to look at the actual amounts of time. And so, while complexity is not maybe the right metric, whatever processing you have, it has to be done within a certain window. Otherwise, you don't get the benefits of real-time operation here. And then, and so the benefits of this is that, while the training setup we did with the channel, with the optimum kinds of beamforming, in the actual operation of the system, we don't do that next level of channel estimation and feedback for the purpose of doing the beamforming. And so the base station can do whatever it wants, and the users, and it doesn't change the standard there. And then we keep continuously updating the code books based on the users that are coming and going over time. And then I'm about done here. So just, in terms of feasibility, I mean, the system, so this is the processing done at the base station. And then, so we did some execution time calculations, and the key here is that this was done with on a workstation that has a top-end NVIDIA 3090, but just one of these graphics cards, and then using TensorRT with 32-bit floating point. And to do this, we're able to do the inference very quickly, in the order of millisecond, which is enough that we can meet the timing requirement. And this sort of hardware capability is something you could imagine having at the edge. I mean, it is one, graphics card after all. And then just to give some highlights of the kinds of results that we get. When we use the optimized code books, we see at the end about a 10 dB improvement over the de facto DFT types of code books, an average RSRP, and then in terms of the actual performance as a function of beam, once we do the beamforming, about a 5 dB gain over doing the multi-user beamforming with the results from the DFT beams versus the results from the from our encoder. And then we also compare with where full CSIT is available, and that's the green curves. And so our approach is the orange, and then the blue is the baseline strategy. And so, yeah, in general, we get, I mean, several dB of improvement. And then we also end up with a code book that it has a bit more of uniform property than just using DFT beams, which typically is only a few beams that are reported well. And then there's some other results as well, which are downlink rates at low and high SNRs. And you know, the punchlines here is that, so the dashed lines are the with the perfect CSI, and then the solid lines kind of in the middle are our approaches, and then the ones on the left are with the DFT type approaches. And so you can see the depending on where you want to look in the CDF curve, you know, substantial gains of, you know, 2 to 4x in terms of rate, depending on where you look. And that can be substantial even with just the SSV8 is just the feedback of basically just doing eight beams of worth of training. So it's quite substantial. And then, yeah, so that's I think I got the key ideas there. You can see that I didn't practice the presentation and realize that there were animations. I was just looking at the slides. So that's it here. And then, you know, just that we are looking at a lot of extensions right now. The one to the wideband case is done, and we're just resimulating everything. And then we're looking at doing the same approach for millimeter wave massive MIMO, trying to do the same trick where we make minimal or no changes in the 5G spec, and then see what kind of rate performance we can get by doing this optimization. And then naturally here at this conference, you know, with so many stochastic geometry people, is it begs the question of where was the interference, and sadly there was no interference here. So that's definitely a limitation of this initial data set we've collected. And so we do need to do something with other kinds of interference. Though interference is not here, we did have use results with very low SNRs. So I do feel like there's not, I feel like it's still going to work. But of course, when you have interference, you can get interesting temporal behaviors and ping-ponging that you wouldn't get, you know, without the interference. So that's I think the most important extension that we need to consider. And then just, yeah, to summarize here, I mean, this beam-based approach, it's splitting the beamforming in analog and digital. It becomes more challenging to configure the analog. The vehicular communication setting, it's an opportunity because there's a lot of data. It's also challenging because things are moving quickly. And we've provided some evidence that this machine learning approach, even without changing the standard, can give better performance. And so, of course, it begs the question of if you can make changes, you know, how could 6G be engineered to work even better? And I'll stop and take any questions if there's any time. Thank you.
Thank you very much. That's fantastic. We have time for a couple of questions. So, Vitaly, please.
Thank you very much, Professor. It's good that are here. So, should I come there?
Okay, come close.
Can you hear me?
I can hear if I turn my volume up. Yeah, I can hear.
So, just speaking about, say, 6G or maybe later 5G releases, if you could name or a couple of things that where you believe the beam management could be done considerably better, like some things you would really love to see relaxed or modified in the cellular system design, which of those would be your top choice? Thank you.
Well, I think just so what we can see is that we can get away with, if we can design different beam patterns, then it does open the door to using more compressive channel estimation techniques that don't work well with pointy beams. but then that has other ramifications and other kinds of system properties. So I would like to, though, still explore that further to see what capabilities might need to be included if we're going to take advantage of and do something that leverages that compressive capability better, because maybe it's not specified in the standard that you have to use, you know, OMP to do this channel estimation, but it would be interesting to see what further can be done. But then when I look at the results from the last part of the presentation where we didn't at the end do the channel estimation and it still works really well, then I say, well, but maybe, I don't know, I need to see. But that's the main thing, is I want to see how to get away from directional beams, the other implications on the system, and then what how that would impact the use of MIMO at the even lower frequencies, the mid band, 10 gigahertz and above, you know, to 300.
Thank you very much.
Thanks. Any other questions? We have Francois to ask.
So thanks, Robert, for the very nice presentation. I was wondering, so if you take a typical scenario with, I don't know, multi-lanes and one base station is, so what is the frequency at which for at nominal velocity you would have to change the, to update, I mean, the beam structure? So because obstacles will change, if I get it correctly. So any configuration will change at a certain pace, right? And so you have to, you will apply your, if I get it correctly, your machine learning and try to for any new configuration. But how often configuration change is a question, and how often do you have to call this to re-update the beam pattern?
Yeah.
Hope my question makes sense.
Yeah, no, it makes sense. And I think part of that is one of the things that we addressed early on in the project with Toyota was defining something that we called beam coherence as a way to say, okay, here's how long one particular beam might work well. And the net of it was that a beam might work well for like 100 small scale coherence intervals. Now, of course, at millimeter wave, the coherence time can, without beamforming, can be very small, but with the beam, it can be larger. So you know, you don't necessarily need to switch the beam every millisecond. And that's why the standard, in addition to initial access, there's also various stages of other parts of beam management I didn't talk about, like the refinement and the tracking. I haven't worked so much on that. Professor Gonzalez-Prochich had a student, and so she's done some work there, and there's others that have looked at that too. So I would say that, and you can still use position information. All of this can be used exactly in that framework. It's just the problem formulation is a little bit different, because now you're saying, okay, based on the previous beam that worked and where I am now, do I want to change the beam or not? So I think it would work there, but we looked mostly at the case where we have the location and we want to, and the site information, and we want to initialize a beam. And then we imagine redoing that every, maybe that's redone every 20 or 100 milliseconds. And then maybe in the middle, you've got another stage of tracking, which is also influenced by machine learning that I haven't developed and I didn't talk about. And I think that's the right timescales. I mean, it's in the, it's in the hundreds of milliseconds of times. But if you refine and have a super pointy beam, of course it can need to be repointed less than that. And if you have a wide beam, it can be good for tens of seconds.
Thank you. Thank you. If there is no other question, I have a quick one, very quick one, a bit provocative. Any idea why the code book generated by machine learning work better? Because if we can get an idea of why, we may reuse this information to build code books.
No, I mean, we know well why, because even from the earlier study, if I go back even just to, I mean, as far as specifically why in the latter case, I don't know exactly there, because the results there are newer, but just going back to like this picture here. So we have planar arrays, and the importance of elevation, it really varies depending on the application, right? Like, I mean, if you have a planar array and you're supporting a street, it's mostly the elevation is mostly pointing down, right? So if you have a DFT codebook where you're uniformly quantizing both azimuth and elevation angles, well, there's a whole bunch of angles that you're not using. I mean, unless you have UAVs. If you don't have UAVs, all the angles that point up are kind of gone, right? So that's part of it. And then with the cars, the cars are only using certain combinations of beam patterns, and that's what's illustrated in this AOD distribution. And so a DFT type codebook would be uniformly quantizing this picture, but we can see that uniform is a horrible design here. And maybe you want maybe there's people on the sidewalk, and so maybe it needs to be a little more uniform. But I think that's the first thing, is that the not all the angles are just equally employed. And then another thing is that this is site specific. So I could have a planar array in a different part of the city that is serving people in a residential area, and we do need those elevation angles. And so, like, a uniform quantization is great because it'll work everywhere. It just doesn't work well anywhere. So you might need a different one there. And so then this kind of begs the question of, well, okay, but maybe I need one set of code books for the roads and another set for this residential area. And then there's opportunities for looking at like transfer learning. How do you take advantage of what you learned here and use it over there? But that's my intuition here. And then in the other case, with the lower frequency, I don't have as much insight there. I mean, we are using planar arrays at both sides, and we're using the Quadriga model with some modifications that, I mean, it's an incredibly rich model. It's not just doing ray tracing. So there's a lot of scattering and angle spread and clusters. And so I'm surprised it works as well as it does there, actually. But I think it's the similar reason here, because we are testing, in kind of the same environment. We're not like generating testing data here and then going to a different city, well, not training in one city and testing in another, let's say.
Okay, thank you very much. I think in the interest of time, we have to stop here.